Download this code from codegive.com, link in the description below. OK, let's delve into the world of complete graphs in discrete mathematics, covering their properties, characteristics, representations, and even some basic code examples to visualize them. What is a complete graph? In graph theory, a complete graph is a simple indirect graph where every pair of distinct vertices is connected by a unique edge. In other words, every vertex has an edge to every other vertex in the graph. It's the densest possible indirect graph. Key properties and characteristics asterisk. 1 notation asterisk. A complete graph with n vertices is denoted as k sub n/sub. 2 number of vertices and edges asterisk. Asterisk. A complete graph k sub n/sub has n vertices. Asterisk. The number of edges in k sub n/sub can be calculated using the formula n asterisk n 1/2. This is because each of the n vertices is connected to n1 other vertices. We divide by 2 to avoid double counting each edge, since the graph is indirect. This formula is also the same as the number of combinations of choosing 2 vertices from n vertices, sup n/sup c sub 2/sub or, and choose 2. 3 regularity asterisk. A complete graph is a regular graph. A graph is k-regular if every vertex has degree k. In a complete graph k sub n/sub, every vertex has degree n1. Therefore, k sub n/sub is an n1 regular graph. 4 cliques asterisk. A clique in a graph is a subgraph where every pair of vertices is connected by an edge. A complete graph k sub n/sub is a clique of size n within itself. It's the largest possible clique within its own structure. 5 connectedness asterisk. Complete graphs are always connected. Since every vertex is connected to every other vertex, there is a path between any 2 vertices in the graph. 6 diameter asterisk. The diameter of a graph is the longest of all the shortest paths between any 2 vertices. The diameter of a complete graph is always 1. This is because you can go directly from any vertex to any other vertex in a single step, edge. 7 Hamiltonian cycle and Eulerian cycle asterisk. Asterisk. A Hamiltonian cycle is a cycle that visits every vertex exactly once. Complete graphs k sub n/sub for n equals 3 always have a Hamiltonian cycle. In fact, they have many. Asterisk. An Eulerian cycle is a cycle that visits every edge exactly once. Complete graphs k sub n/sub have an Eulerian cycle if and only if n is odd. This is because a graph has an Eulerian cycle if and only if every vertex has an even degree. The degree of each vertex in a complete graph is n1, so n1 must be even, implying that n is odd. 8 Planarity asterisk. A graph is planar if it can be drawn on a plane without any edges crossing. Asterisk. K sub 1/sub, k sub 2/sub, k sub 3/sub, and k sub 4/sub are planar graphs. Asterisk. K sub 5/sub is non-planar. It's one of the 2 Kuratowski graphs that are used to characterize planar graphs. Kuratowski's theorem states that a graph is planar if and only if it does not contain a subgraph that is a subdivision of k sub 5/sub or k sub 3,3/sub. Asterisk. For n4, k sub n/sub is non-planar. 9 Chromatic number asterisk. The chromatic number of a graph is the minimum number of colors needed to color the vertices of the graph such that no 2 adjacent vertices have the same color. The chromatic number of k sub n/sub is n. You need a different color for each vertex. 10 Applications asterisk. Complete graphs, while seemingly simple, have applications in various fields. Asterisk. Networking asterisk. Modeling fully connected networks where every device is directly connected to every other device. Asterisk. Social networks asterisk. Representing groups where every member is acquainted with every other member. Asterisk algorithms asterisk used as building blocks in certain graph algorithms. Asterisk tournament scheduling asterisk to represent every team playing every other team once. Representing complete graphs asterisk. There are several ways to represent graphs, and these apply to complete graphs as well. 1. Adjacency matrix asterisk. Asterisk an nxn matrix where the entry at I, j is 1 if there is an edge between vertex I and vertex j, and 0 otherwise. For a complete graph, all entries except the diagonal elements, which are typically 0 for simple graphs, will be 1. 2. Adjacency list asterisk. Asterisk a list where each vertex has a list of its adjacent vertices. In a complete graph, the adjacency list for each vertex will contain all other vertices in the graph. 3. Edge list asterisk. Asterisk a list of all the edges in the graph. Each edge is represented as a pair of vertices. Code examples, Python with NetworkX and Matplotlib. Here's how you can create and visualize complete graphs using Python with the networks and Matplotlib libraries. First, make sure you have these libraries installed. Here's the Python code. Explanation of the code asterisk. 1. Create _complete _graph, n, asterisk. Asterisk this function utilizes networks' built-in nx.complete _graph, n, function. This efficiently creates a complete graph with n nodes. 2. Visualize _graph, graph, asterisk. Asterisk this function takes a networkx graph object as input. Asterisk nx.spring _layout, graph, calculates node positions in a way that attempts to minimize edge crossings and produce a more visually appealing layout. You can experiment with other layout algorithms like nx.circular _layout, graph, for different arrangements. Asterisk nx.draw, draws the graph using Matplotlib. We customize the appearance with options like asterisk with _labels equals true, displays the vertex labels. Asterisk node _color equals sky blue, sets the color of the nodes. Asterisk node _size equals 800, sets the size of the nodes. Asterisk font _size equals 12, sets the font size for the labels. Asterisk font _weight equals bold, makes the labels bold. Asterisk plt.title, adds a title to the plot. Asterisk plt.show, displays the plot. 3. Complete _graph _adjacency _matrix, n, asterisk. Asterisk this function constructs an adjacency matrix representation of the complete graph. The matrix is built using nested list comprehensions. For each row and column, ij, it checks if I is not equal to j. If they are different, it sets the matrix element to 1, representing an edge, otherwise, it sets it to 0, no edge or self-loop. 4. Complete _graph _adjacency _list, n, asterisk. Asterisk this function creates an adjacency list for the complete graph. The outer dictionary comprehension iterates through each vertex, I, and maps it to a list of its neighbors. The inner list comprehension generates the list of neighbors for each vertex, I, including all other vertices, j, except itself, where I, equals j. 5. Complete _graph _edge _list, n, asterisk. Asterisk this function creates an edge list for the complete graph. The list comprehension iterates through each pair of vertices, I, j, and creates an edge, ensuring that I is less than j to avoid creating duplicate edges, example both, 1, 2, and 2, 1, since the graph is undirected. The result is a list of tuples, each representing an edge in the graph. How to run the code asterisk. 1. Save the code as a Python file, example complete_graph.py. 2. Open a terminal or command prompt. 3. Navigate to the directory where you saved the file. 4. Run the script, python complete_graph.py. This will create a complete graph with 5 vertices. You can change the value of n_vertices. Display a visualization of the complete graph in a matplotlib window. Print the adjacency matrix representation of the complete graph to the console. Print the adjacency list representation of the complete graph to the console. Print the edge list representation of the complete graph to the console. Print the number of edges. Further exploration vary the number of vertices. Experiment with different values of n_vertices to see how the complete graph changes. Change layouts. Try different layout algorithms in visualize_graph. Example nx.circular_layout, nx.random_layout, nx.shell_layout. Implement graph algorithms. Implement algorithms like finding Hamiltonian cycles or testing for planarity on complete graphs. Note: testing for planarity on ksubn/sub for larger n is trivial, it's nonplanar for n4, but the implementation would be more general for other graph types. Explore other graph types. After understanding complete graphs, explore other types of graphs like bipartite graphs, trees, cycles, etc. Network X documentation. Refer to the Network X documentation for a comprehensive overview of the library's capabilities. https://networks.org/ https://networkx.org. Complete graphs are a fundamental concept in graph theory. Understanding their properties and representations is crucial for working with more complex graph algorithms and applications. The Python code provided gives you a practical way to create, visualize, and manipulate complete graphs, allowing you to solidify your understanding and explore further. Good luck.